Hello everyone. So this is the final topic of the module one, that is signal flow graphs. It is very similar to the block diagram representation, but it will looks a little bit of different. When you see that one, then you can understand. So the signal flow graphs and what are the concepts and what is the Mason-Did formula, where it is used to reduce the total signal flow graphs into small signal flow graphs. Okay, the topics to be covered is signal flow graphs in this one, and the next continuation how it is reduced according to the Mason-Did formula. Okay, so what is a signal flow graph means? It is simply, if you see here, this is the representation of the signal flow graph. So whether you can see like it as a, if the B and C, D, E are, we can take it like it as a blocks also. In generally, what is the basic similarities means these may be the block, these may be the different. But if you see, these type of things cannot be happen in the block diagram. So wherever this F blocks is there, the same in between internally rotating things, this is not happening there. So these type of things will not happen in there, but only the signal flow graphs will happen. These type of graph representations are called signal flow graph. In a normal understanding, a signal flow graphs will be representing as a SFG. Is a graphical representation of a set of linear algebraic equations. Okay, it's a linear algebraic equation, and it shows the how variable it shows influence on each and one another using nodes and branches. The only the difference is there the nodes and branches will not be there in the block diagram presentation, but here they plays a major role because here when I will tell you whenever it is happening there, when we're reducing, we need to write what are the number of how many number of branches, how many number of nodes, how many number of tweaks, and everything we need to write. Then only the formula can be able to done. The formula can able to reduce and it will give a good number. Okay. So why we need to use the signal flow graphs? Because signal flow graphs are used in many places, and also they can be directly implementation of the system equations. It is not something like that. Some are reduced, some are not reduced. If you see to the block diagram presentation, they may go before and after, and also some of the transfer functions, some may we can neglect and everything. But signal flow graphs, it is not like that. It will be the direct representation of the system equations, and useful for the whenever you are having multiple inputs and multiple outputs are there, then we can have this type of graphs to understand with a less number of linings and representations, often more intuitive than block diagrams in complex interactions, but not in a very small. When it you go to the complexity, then you can use this signal flow graphs. So components of a signal flow graph is each signal flow graph consists of the nodes that represents the variables. If we, for example, A, B, C, D, E, F, G, so that type of the it represents the number of nodes. It is representing number of system variables. Okay, and the directed branches will be influencing the directed branches, whatever it is, that will be related to the functional dependency with the gain. That is very most important in that one, gain. And the next one is the input and output node. These diagrams are especially used for the Laplace domain. As we already know, Laplace domain will needed like it as a input need to be there and also output need to be there. So regarding that one, we need to have this information, input and output nodes. Okay, let's see with one example, constructing a simple example. I'm just giving a simple example to understand what how exactly the SFG can be done. Okay, so simply if you see here, suppose we have a we have these equation x2 a x1. Okay, let's take it as a x2 and x1. Okay, as they are in a, that means it is in between, it will be there, right? So that means a will be this. So x2 equal to a into x1. Okay, that representation can done. Or sorry, x1 will be here. Sorry, x1 will be here, x2 will be here. Then only that arrow mark will be represented. Then what are they saying? X3 equal to bx2. X3 equal to bx2. That means let's take it as a x3, which will be equal to, this is x3, that is bx2, and the next x4 equal to x4 is equals to cx3, x4 equals to x4 equal to cx3. Okay, so this is the representation what they give. We can draw the nodes for x1 to x4. So x1 to x4, x1 to x4, all the nodes are there. So these are the 1 node, 2, 3, 4 nodes. So connect them with the gains of ABC. As we already connected, A is one gain and B is another gain and the C is another gain. So these type of representation will happen So this is a simple signal flow graphs. So in the next video, we will see examples with the signal flow graphs and also Mason Green formula, how we implement it and how these nodes are branches numbers is very much important on reducing that. Okay. Thank you.